Hello, this is Eloisa with Math Leopard. Today I'm going to solve for the arc length of a parametric curve using most of the concepts learned in second semester calculus. To begin, let's consider the curve defined with a parameter t given by x is equals to the square root of t and y is equals to 3t minus 2. We wish to find the length of the curve for t between 0 and 1. In order to visualize this curve, let's eliminate the parameter as follows. We see that x squared is equals to t, which implies that y is equals to 3x squared minus 2. That is, a parabola stretched vertically by a factor of 3, then shifted down 2 units from the origin, as seen here in the dashed blue image. We note, however, that the domain of the function for x is such that the independent variable t must be greater than or equals to 0. Hence we have only that part of the parabola for which x itself is greater than or equals to 0, seen here as the solid blue line. Given the restriction of t between 0 and 1, the length of the arc we are concerning ourselves with is seen here in purple, between the coordinates 0, -2 and 1, 1. In order to find the formula for arc length, we take a small yet measurable portion of our arc and zoom in. We note that it's approximately linear between its two endpoints, x1, y1 and x2, y2, respectively. Hence we know that the total arc length, denoted by capital L, is equivalent to the sum of these partitions of our curve, namely the sum of each of the distances between their respective endpoints. We recall that the distance formula is given by the Pythagorean theorem as a square root of the quantity x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. I chose these line segments such that they were measurable, hence we can rewrite the squares of the change in both x and y as quantity delta x squared and quantity delta y squared, respectively. Taking the limit as the number of partitions increases without bound, we note that our measurable terms, annotated in Greek, change to their immeasurable equivalents in English. Hence the limit of the sum, sigma, becomes the integral, or an elongated s, and the delta y and delta x become dy and dx, respectively. Note that the limits of integration are from 0 to 1, as our goal is to integrate with respect to the parameter t. As there is no variable by which to evaluate this integral, I multiply the integrand by 1, a very specific one, namely the ratio of dt over dt. Next we push the dt in the denominator under the radical, and hence square it. This results in division by dt squared of each term inside the square root, which in more simplified form gives us the square root of dx dt quantity squared plus dy dt quantity squared as our integrand. Returning to the parametric equations on top, we note that x is given as the square root of t, hence the derivative of x with respect to t, that is dx dt, is 1/2 t raised to the negative 1/2, which implies that dx dt quantity squared will be 1/4 t to the negative first power. Similarly, given that y is equals to 3t minus 2, we have that the derivative of y with respect to t, that is dy dt, is 3. Hence, dy dt quantity squared is 9. Plugging this into our integrand, we now have the integral from 0 to 1 of the square root of 1/4 t to the negative first power plus 9 dt. As I'm not partial to fractions, let's factor the 1/4 out from under the radical as 1/2. Meaning we must multiply each term inside the radical by 4, leaving us with t to the negative first plus 36 inside. Going forward, I'm going to pull the constant out in front of the integral, hence we have 1/2 in front at this point. I note that 36 is a perfect square, as is t inverse, namely they are 6 and t to the negative 1/2 squared, respectively. This is a sum of squares and hence indicates a trigonometric substitution of tangent. That is, we let t to the negative 1/2 power be equals to 6 tangent of theta, seen here on the right in light green. Taking the derivative of both sides, we have that negative 1/2 t to the negative 3/2 dt will be equals to 6 secant squared theta d theta. However, I can simultaneously multiply the equation by negative 2 and rewrite t to the minus 3/2 as quantity t to the minus 1/2 cubed, leaving me with negative 12 secant squared theta on the right. However, t to the minus 1/2 was equivalent to 6 tangent of theta by construction. Hence we have the quantity 6 tangent of theta cubed dt is equals to negative 12 secant squared theta d theta. dividing both sides by the cube of 6 tangent theta, and rewriting negative 12 as the product of negative 6 and 2, we have that dt will be equals to negative 6 times 2 secant squared theta divided by 6 times 6 squared tangent squared theta times tangent of theta. That is, I broke up the cubes of both 6 and tangent in order to more easily simplify the quotient. We see that the leading 6's reduce, and note that 2 over 6 squared, or 2 over 36, reduces to 1/18. We also note that secant is a reciprocal of cosine, and tangent is sine times the reciprocal of cosine. Hence their quotient reduces to the reciprocal of sine, namely cosecant. In this case, both secant and tangent were squared, hence we simplify to cosecant squared. Finally, the reciprocal of tangent is cotangent. Thus we have that dt is negative 1/18 cosecant squared theta cotangent theta d theta. With trigonometric substitutions, we draw the corresponding right triangle to that substitution. Namely, given an angle theta, we know that tangent of theta is defined as sine of theta over cosine of theta. Or more colloquially, the opposite side, t raised to the negative 1/2, divided by the adjacent side, 6. Hence, by the Pythagorean theorem, the hypotenuse is given as a square root of quantity t to the negative 1/2 squared plus 6 squared, which was our integrand. But what is the integrand in trigonometric form? We know that t to the negative 1/2 power is equivalent to 6 tangent theta. So replacing this under the radical gives us 36 tangent squared theta plus 36 when we square 6. Factoring the 36 out from under the root as 6, we're left with the square root of tangent squared theta plus 1. That is, our integrand simplifies to 6 secant theta, because of course tangent squared theta plus 1 is secant squared theta. Replacing our integrand with 6 secant theta and dt with negative 1/18 cosecant squared theta cotangent theta d theta, we have a temporarily indefinite integral entirely in terms of theta. And please, I beg of you, refrain from including multiple variables within a single integral. Continuing on, we see that the constants 1/2, 6, and negative 1/18 reduce to negative 1/6, which I place in front of the integral, and what remains is cosecant cubed of theta, because as we know now, the quotient of secant and tangent, which is equivalent to the product of secant and cotangent, is cosecant. When given either cosecant cubed theta or secant cubed theta, the most logical way to proceed is with integration by parts. Hence, we let u be equal to cosecant theta and dv be equals to minus cosecant squared theta d theta. The derivative of cosecant theta du is equal to minus cosecant theta cotangent theta d theta. And the antiderivative of minus cosecant squared theta d theta, v, is equals to cotangent of theta. I'm going to call the negative 1/6 times the integral of cosecant cubed theta d theta capital I. Hence, I will be equals to positive 1/6 because I use the negative to define dv times the quantity uv, or cosecant theta times cotangent theta, minus the integral of v du, or cotangent theta times the quantity negative cosecant theta cotangent theta d theta. Factoring out the negative and rearranging the second integral, we have that I is equals to 1/6 the quantity cosecant theta cotangent theta plus the integral of cosecant theta times cotangent squared theta d theta. But by the Pythagorean identities, I know that cotangent squared theta can be rewritten in terms of cosecant theta as quantity cosecant squared theta minus 1. Distributing the 1/6 and breaking the integral into two separate integrals, we have 1/6 cosecant theta cotangent theta plus 1/6 the integral of cosecant cubed theta d theta minus 1/6 times the integral of cosecant theta d theta. We note that 1/6 the integral of cosecant cubed theta d theta is equivalent to the negative of our integral and left-hand side of the equation, capital I. Hence, adding I to both sides leaves us with twice I is equals to 1/6 cosecant theta cotangent theta minus 1/6 the integral of cosecant theta d theta. I'm going to simultaneously solve for I by dividing by 2, and then multiply the integrand of the integral on the right by 1. This leaves me with a coefficient of 1/12 in front of each term. To integrate cosecant of theta, it would be easier if I had either minus cosecant squared of theta or minus cosecant of theta cotangent of theta, as those are both with the two standard derivatives involving cosecant. Hence I'm going to multiply by the sum of cosecant of theta and cotangent of theta divided by that same sum, namely a very specific 1. What this does is give us the two derivatives involving cosecant in the numerator. That is minus cosecant squared of theta and minus cosecant of theta cotangent of theta, and their corresponding antiderivatives in the denominator, cotangent of theta and cosecant of theta when the order is rearranged. So I see that if I let w be equals to the denominator cotangent of theta plus cosecant of theta, seen here in pink off to the right, then the derivative dw will be equal to the numerator, that is minus cosecant squared of theta minus cosecant of theta cotangent of theta d theta. Hence we can rewrite the integrand of our indefinite integral as dw over w. We know that the antiderivative of 1 over w is natural log of absolute w, where w was the placeholder for cosecant of theta plus cotangent of theta. Finally, I'd like to return to an expression in t, as that is a variable with which our definite integral is defined. This is where we use a triangle to change from trigonometric form back to t. The first term has a factor of cosecant of theta and cotangent of theta. Cosecant of theta is the reciprocal to sine of theta, hence is the ratio of the hypotenuse to the opposite side, or the quotient of a square root of quantity t raised to the negative 1/2 squared plus 6 squared over t raised to the negative 1/2. Cotangent of theta is the ratio of cosine of theta over sine of theta, hence is the quotient of adjacent side over opposite side, namely 6 over t raised to the negative 1/2 power. We can now reintroduce the limits of integration from 0 to 1. When we add 1/12 times the quantity natural log of the absolute value of cosecant of theta, which we know to be the square root of t raised to the negative 1/2 quantity squared plus 6 squared over t raised to the negative 1/2 plus cotangent of theta, or 6 over t raised to the negative 1/2, also evaluated from 0 to 1. Before I plug in the limits of integration, I'd like to simplify by eliminating the negative exponents. I see in the first term 2 instances of t raised to the negative 1/2 in the denominator, which have a product of t raised to the negative first. Hence, when pushed across a division symbol into the numerator, becomes t. We then move inside the logarithm and see that t raised to the negative 1/2 is equivalent to the square root of t in the numerators. But this still leaves me with the negative exponents underneath the square roots. In order to eliminate these, in the first term I push t inside the radical, hence he becomes t squared, reducing the first term to t and the second to 36t squared. Similarly, I push the square root of t underneath the root in the first term inside the logarithm, and hence it becomes t, reducing the first term to 1 and the second to 36t. At this point there are no more negative exponents, so I can evaluate this expression at its limits of integration. Before doing too much work, too late I know, I note that if I were to plug in 0, that both terms underneath the radical would sum to 0 in the first term, and the sum inside the logarithm would be equals to 1, and hence that term would also be 0. So I can save myself the time of writing it out and simply plug in 1. Hence we arrive at 1/12 the quantity, 6 times the square root of 1 plus 36 or 37, plus natural log of the quantity, square root of 1 plus 36 or 37, plus 6 times the square root of 1, or 6. Therefore, the arc length for this parametric curve is given as 1/2 square root of 37 plus natural log of the 12th root of the quantity, square root of 37 plus 6. Thus it is shown. Thanks for playing, and I'll see you next time.